So, welcome again to the module 2 lecture 8 of RF transceiver design. We are discussing noise. We will also discuss noise in more detail. So, we in the last class we have this equation that we have discussed about the power spectral density of thermal noise and various units also we have discussed in last class. So, the white noise is of uh, resistor can be given by 4 kTr or thermal noise can also be written in terms of 4 kTr. It is independent of frequency, that is why it is called a white. So, the term white is coming because it is a independent of frequency. So, we were at this equation in the last class that if there is a noisy resistor that is given and that noisy resistor how much noise power it will transfer, and the final equation is a KTB. Now, this equation is important, it will give us the understanding of how the noise performance with respect to the bandwidth and temperature will be. So, if you have very smaller bandwidth, let us say if your system has a smaller bandwidth, then noise power is less. So, you can also write that bandwidth, if your bandwidth is smaller, there is a less noise power. So, as in current RF system we are increasing the bandwidth high and high. So, there is a power will also noise power will also increase. So, there is always a trade off between bandwidth and noise. So, it will also tell us what is the trade off. If you have a bandwidth is increasing, your noise power will increase. Another important feature is a temperature. If you increase the temperature, then your noise power will increase, and if you reduce the temperature, your noise power will decrease. So, for you can also nowadays we are also using RF systems or RF components for superconducting application also, where when we are trying to reduce the temperature, your noise power is also reducing, and if you increase the bandwidth to infinite, your noise power will also increase to infinite. So, always keep in your mind that your noise is proportional to temperature and bandwidth. So, if noise power is denoted by N naught and equivalent temperature of Te, then output power N naught is also mentioned in terms of KTEB, or equivalent noise temperature can also be given by N naught by KB. So, you can also represent the noise in terms of equivalent temperature or in terms of the power. So, in various application there is a different way of convention that we are also representing noise as a equivalent temperature. Now, let us say I have some amplifier and the amplifier has a gain of G, and I have input noise power that is a N naught. So, what is your output? Obviously, it will have a gain which is added. So, your output power is nothing but GKTB. So, it is multiplied with the gain. So, if you also want to represent any amplifier with the equivalent temperature Te, then you should write N naught by GKB. So, this is for the amplifier with a gain of G, and there is a various active noise source are also available, and that active noise source has a excess noise ratio has been defined, and this active noise source are made of I think diode, tube or solid state devices, and it is very useful in measurement. When you want to find out the noise parameters of any system or your devices, then this active noise source are used, and it is a term that is defined, that is a excess noise ratio. So, excess noise ratio is with respect to the temperature T naught, and it can be given by the uh, manufacturer, that what is the ENR of certain active noise sources, that is the equation is 10 log Tg minus T naught by T naught. Here Ng is the noise power from the generator means which is a active source, and N naught is the noise power from 50 ohm impedance at a room temperature. So, this is defined. We will also see in detail when we discuss the noise figure how this excess ENR is used to find the noise figure of any device under test. Now, let us take an example. So, this Y factor method is also widely used to find the to measure the noise temperature. So, how exactly how it will work? There is a device under test for which we want to find the noise, and that is a equivalent temperature Te. So, generally what it is considered, that first you connect your input to the hot source, that is a T1, that is a temperature T1, and you know the temperature T1, and then you find the value of N1. After that you connect the hot source to the cold source, and then you find the output power N2. So, you get output power N1 and N2, and the ratio of N1 and N2 will give you the Y factor. So, here when you connect the your resistance hot load at T1 temperature, then what is the N1? So, you should write N1 which is equal to G K T1B plus G K TEB, because this input temperature will also get the gain of G, then you will get the, then you connect to the another load, that is at temperature T2, and that is the cold. So, generally in this you can also consider that if your resistor is in liquid helium or liquid nitrogen, and in other case it is different temperature. So, helium nitrogen has a different temperature. So, then there is a output N2, that is given by Gk T2B plus Gk TEB. We can divide N1. So, this is equation 1, this is equation 2. So, by using equation 1 and 2, if we find the factor N1 by N2, this is nothing but the Y factor, which is given as a, so Gk is a common. So, you can write a Gk B into T1 plus Te by Gkb T2 plus Te. You can cancel out this Gkb. So, this is given as a T1 plus Te by T2 plus Te. So, you can write it down Te, which is equal to T1 minus Y T2 upon Y minus 1. So, for finding out the correct Te, what is the condition? Your T1 should be much greater than T2, then only you will get the Y sufficient, because if Y is equivalent to 1, then you cannot find the Te. So, in order to get the accurate value, the difference in the temperature should be as high as possible. So, this is how the Y factor methods are used to find the noise temperature. So, How you will get the y? You will get the y from this N1 and N2, you will find out the equivalent noise temperature. We will also try to see the example, because when we see the example we will get the more idea about how the equation works. So, in this example what exactly has been given, that there is a amplifier which is working at X band. It has a gain of 20 dB, it has a bandwidth of 1 gigahertz, and then find the equivalent temperature using the Y factor method with the following data. So, what is the data is given? So, now when you try to measure, first you connect with the T1 at 290 Kelvin and find out the output noise power N1, and then you find the then you apply the another switch, apply to the T2 at 77 Kelvin and find out the output power N2. So, this is a measurement that you should do. Now, what you are interested to find the equivalent temperature TE. So, first of all you get a Y which is N1 by N2. You can, if you write in dB, it is N1 minus N2, you will roughly get the value of 2.7 dB. Then you use the equation, equivalent temperature equation TE, that is T1 minus Y T2 by Y minus 1. This 2.7 dB you need to convert into absolute term, that will come around 1.86. So, you will get the T1 you should use a 290 and T2 you should use a 77 Kelvin, you will get equivalent temperature around 170 Kelvin. So, this is how you can find the equivalent temperature of any device under test by using a Y factor method. And then what is another question, that what you want to find is a noise output power. So, if you want to find the noise output power for the same, what can be written, that is a GKTSP plus GKTEB. So, you can also write, so in this example if I have a certain source temperature Ts, so this is an amplifier, and if certain source temperature, that is means one resistor Rs is connected and its source temperature is Ts, then I can write the output N naught is GKTSB plus GKTEB. So, GKB you already know, you can put Ts plus Te, and if your Ts is, for example, it is a 450 Kelvin, so you will get a, you just try to put 450 Kelvin, then Te that you got 170 Kelvin, and put all the value gain and bandwidth, you will get the output noise power around minus 60.7 dBm. So, this is what you will get, that is the output noise power. So, in this example what we try to understand, that if we have any device under test, first we can find out the what is the equivalent temperature, and then if any other temperature input, means with different temperature source is given, you can find the output noise power. So, this is how you can use a Y factor method. Now, we will define the important term for any RF system, that is a noise figure. What exactly noise figure is? It measures the degradation of the signal to noise ratio SNR between the input and output of the system. So, how exactly the signal to noise ratio is defined? There is a signal power divided by the noise power. Now, let us say if you have a noiseless system and if you have given certain SNR input, this is a SNR. If you have given a certain SNR input Si by Ni and there is a noiseless source, noiseless system, then because it is not adding any noise. So, what you will get at output? Your signal will amplified with and the gain of the system is G, for example. Then your signal will amplified with the gain. So, the what is the output SNR? Output, what is the output SNR? SNR out, that is SO by NO. SO is nothing but gain into SI, means your input as a multiplied with the gain, and what is the NO? That is a gain into NI. Now, what is happening here? That this is your SNR in, which is SI by NI, and this is your SNR out, which is SO by NO, but because there is a gain, both gain will be cancelled out, it can also given as the SI by NI. So, what it says that if you do not, if your system does not add any noise, your SNR input is equal to SNR output. So, there is a no degradation in your signal to noise ratio. So, what exactly noise figure is? It measures the degradation. If there is a degradation, this SNR in and SNR out, which value is much greater than 1, because there is a noise will be added by this system. So, for ideal system, as I explained, your SNR in by SNR out is equal to 1, but for most of the system it is a greater than or equal to 1. So, what is the equation of noise figure? That is SNR in by SNR out. Now, here in this example what we have considered, that your noise figure, I can also write Si by Ni by SO by NO. So, here Si by Ni, I will rewrite it again with NO by SO. So, Ni, what is the Ni? We already seen it is nothing but K T naught B. So, Si divided by K T naught B into NO. So, NO, what is the NO? The, as we have seen, that is a K T P K T naught P multiplied with the gain plus G K T E B divided by Si. So, here because there is a no any noise is added by the amplifier, what we have considered G into Ni, but when we try to have a noise added by the system, then you need to add the noise of that system, that is G K T E B. So, and what is the SO? SO is nothing but gain multiplied by Si. So, if you rewrite the equation again, this Si will be cancelled out and this Kb will also be cancelled out and your gain is also cancelled out. So, what is the final equation that you get? T naught plus T e by T naught. So, equal to 1 plus T e by T naught. So, this is also called a noise factor f, because it is in absolute term. Noise factor this is a noise factor f, which is equal to 1 plus T e by T naught. We in the last example we already find out the equivalent temperature T e, and we know the T naught, we can easily find the noise factor. Then what is the noise figure? Noise figure is, it is in dB, which is equal to 10 log of f. So, noise figure generally defined in the dB, and the 10 log of this noise factor is nothing but the noise figure. So, this is what is the basic idea behind noise figure. So, if you consider the ideal system, this added GKTEB is not added, then your system has a noise factor which is 1 only. But if there is a noisy system, then there is a degradation in SNR, whatever input SNR it has, and you will get the noise factor more than 1, and noise figure is nothing but 10 log of f, noise factor. Now, when we have only seen the single system, means single amplifier, but in RF system there are many components which is a cascaded, like low noise amplifier, mixers, IF amplifier, filters. So, if there is a cascaded system, then how you can get the noise figure of the complete system. So, for that we will try to find out the noise figure of a cascaded system. So, I have noise input power Ni, and for the first system the gain is E1, the noise factor is F1, equivalent temperature of the system first component is TE1, the output of that is given by N1. Then for the second component, that is noise gain is G2, noise factor is F2, equivalent temperature is TE2, and that is the output of the complete system. Now, if we want to replace this with the equivalent, that is also written as a G cascade, then F cascade and TE equivalent cascade, because we have cascaded the system. So, here it is a G cascade, this is F cascade, and then this is a TE cascade. So, how we can write it down N1, if we want to write it down N1, it is nothing but G1 into K what is N1? N1 is nothing but G into K T naught P, G1 into K T naught B, G1 into K T E B, that is the N1. Then what is the N2? N2, which is equal to G2, means same will be multiplied with the N1, plus it will also add the G2 K. So, here it is a TE1 TE2 B. So, how exactly it is? There is a N1 which is a combination of input power Ni, which is given by G1 k T naught B, and then the equivalent temperature of the first system is a TE1. So, the noise added, which is a G1 k T1 B. Then if you want to find the N2 or N out, in this case it is a N out, which is a G2 into N1 and G2k TE2 B. So, if I will just replace the N1 here, that is a G2 G1 k T naught B plus G1 k TE1 B plus G2 k TE2 B. And if I will take G1 G2 k B out, because which is a common. So, I can write G1, so T naught by G1 G2 k. So, I can write here T naught, because G1 G2 k B T naught plus TE1. So, this is a TE1 plus TE2 G1. So, I hope you understand here what exactly has been considered. This G1 G2 KB is taken out. So, for this it is T naught plus TE1 plus TE2 by G1. So, this is a output power, this is a output noise power of this cascaded system. Now, we want to replace this cascaded system, but because we are interested to find the equivalent noise figure, equivalent noise temperature of the cascaded system, then we will find out the, for this, what is the N naught. So, this is the equation if we give as a 1 for cascaded system, what is the N naught, then if the gain of cascaded system is a G cascaded into Ni, that is k T naught B plus G cascaded k T cascaded, because we are considering the cascaded temperature T cascaded G k T cascaded B. If the G cascaded is equal to G1 plus G2, if G cascaded is equal to G1, because its system is in cascade, we can also write G1 G2 k T naught B plus G1 G2 k T cascaded B. Now, same thing if we try to get G1 G2 KB out, we will get T naught plus T cascade. This is the equation 2. So, based on equation 1 and equation 2. So, based on equation 1 and 2, because we are interested to find the equivalent noise temperature of the cascaded system or noise figure, we just equate both with each other, then we what we will get, T naught plus T cascade equal to T naught plus TE1 plus TE2 by G1. This will be cancelled out, and your T cascade is equal to TE1 plus 1 by G1 TE2. Now we all know what is a T. T denotes what? So our T cascade is equal to TE1 plus 1 by G1 TE2. So what is the relation between the noise figure and temperature is given by TE, which is equal to F minus 1 into T naught. So I just replace this equation in this. So we can write F minus 1. So F cascaded minus 1 T naught, F1 minus 1 into T naught plus F2 minus 1 by G1 into T naught. So we can write F cascade, which is equal to F1 plus F2 minus 1 by G1. So this is very important equation. Now what it says that your cascaded noise figure F is equal to noise figure of first system F1 plus F2 minus 1 by gain of first system. So your cascaded noise figure has a direct relation with the first component of your any receiver system. So here when we are designing the receiver noise figure, the first component is important. And if I will try to elaborate this, that is if F cascade, which is equal to F1 plus F2 minus 1 by G1 plus F3 minus 1 G1 into G2 plus it will go on. Similarly, you can also write T cascade equivalent temperature TE1 plus TE2 by G1 plus TE3 by G1 G2 and it will go on. So this is a very important equation. So this is also called the freeze formula. It is also called the freeze formula for noise cascaded noise figure. And this is very important as far as receiver design is concerned, because your noise figure of complete receiver system is depend upon your first component. So we will try to see more in detail about the noise figure. We will also get the try to solve one example to understand that how the cascaded noise figure can be calculated, because we will get more idea about the equation in the next class. Thank you.